Welcome to The Explainer. Today, we're demystifying a highly efficient modern manufacturing marvel. We're going to look at a process that honestly sounds a little bit like science fiction, but it's actually responsible for creating some of the most critical components in our everyday lives and even up in our skies. We're going to trace the journey of what you might call magic dust and see exactly how it completely transforms modern engineering. Just look at this incredible contrast. Over on the left, you've got this simple, unassuming pile of raw metal dust. I mean, it looks like something a stiff breeze could just blow away, right? But on the right, that exact same dust has been transformed into a heavy-duty, high-performance, incredibly complex gear. There's no giant block of metal being chipped away here. We are literally building up from the tiniest particles imaginable. Well, this magic trick is actually a super precise science known as powder metallurgy, or PM for short. So what is it exactly? By definition, it's a manufacturing process that involves producing metal parts and components entirely from metal powders. It's a wildly versatile and highly cost-effective method for creating complex-shaped, extreme performance parts. Instead of melting massive vats of metal and pouring it, or carving it out of solid blocks, we just start with powder. And this perfectly highlights why PM is widely considered an established green manufacturing technology. You know, when you conventionally cut and mill a piece of metal, you're generating an absolute mountain of scrap and waste. But powder metallurgy, it forms components right into their final, or what we call net or near net shape, right out of the gate. You use exactly the amount of material you need and nothing more. That is a massive win for manufacturing efficiency. Section 1. Everyday and Extreme Applications. Before we dive too deep into the science, let's talk about where these parts actually end up. PM is incredibly versatile. On one hand, you see its massive role in the automotive industry, creating totally critical engine components, transmission parts, and gears. Then, on the other hand, we see incredibly tough industrial cutting tools and pneumatic mufflers. It's wild to think the exact same core process builds the parts that drive your car and the heavy machinery used to build the roads you drive on. But hey, these applications don't stop at ground level. PM actually soars right into the extreme environments of the aerospace industry. It's perfectly suited for forming things like structural parts and turbine blades. Why? Because aerospace demands incredible high-temperature resistance, excellent strength-to-weight ratios, and the ability to produce highly complex geometries. When you're building a jet engine, you need parts that can survive brutal conditions without weighing the aircraft down, and PM delivers exactly that. So, here's a wild thought. PM isn't just for massive heavy machinery or roaring jet engines. It's actually heavily utilized inside the human body. Yep, the medical and dental industries rely on PM for orthopedic prostheses, dental implants, and precision surgical instruments. The reason PM is so ideal here is that we can formulate materials that are uniquely biocompatible, offering excellent strength and the incredible wear resistance you absolutely need for load-bearing applications, like a hip replacement. Now, this kind of wide-ranging versatility across all these different industries is only possible because PM can use pretty much any material you can think of. We're not just talking about your standard ferrous iron and steel, though of course those are heavily used. We can use non-ferrous metals like copper, titanium, and aluminum. We can even process highly advanced superalloys like Inconel or extreme hard materials like tungsten carbides for cutting tools. Basically, if you can turn it into a powder, there's a really good chance you can use it in PM. Section 2. Making the metal powder. Okay, so how do we actually get these ingredients? It's not like you just stumble across bags of titanium dust in the wild, right? There are 5 main methods to source our metallic powder, including chemical techniques, electrolytic methods, and physical fracturing. But out of all of these, the absolute most vital method for mass production is the first one on our list, atomization. Let's put the 2 main atomization methods side by side. The concept here is just wild. You take a stream of violently hot liquid molten metal and shoot it through a tiny orifice. Then you blast that stream to completely break it up into tiny droplets. On the left, you've got gas atomization, where high-pressure jets of inert gas break up the stream. And on the right, you've got water atomization, which uses high-pressure water jets to do the exact same thing. Now, while they might seem pretty similar at first glance, choosing between gas and water drastically changes your final product. Gas atomization typically produces perfectly spherical metal particles. On the flip side, using water allows for much more rapid cooling of the metal slurry. And because water cools that molten metal so incredibly fast, water atomization allows for significantly higher overall production rates. Section 3, the manufacturing process steps. All right, we've got our magic dust. So, how do we turn it into solid stone? Well, the whole operation follows a very strict step-by-step journey, broken down into 5 distinct phases. First, powder preparation. Second, blending. That's where we mix in essential additives and lubricants. Third is compaction, where we force the powder into a shape. Fourth is sintering, which involves heating that compacted shape in a furnace. And finally, step 5 involves any secondary or finishing operations to lock in the exact final tolerances required. If you trace this path from left to right, you can see exactly how those base metal powders are mixed with specific additives and lubricants before moving on to compaction. And check out the options here. Compaction can be done cold or hot, through pressing, rolling, or even injection molding. Once it's compacted, it moves right into the sintering phase in special atmospheres or strict vacuums, before finally heading to secondary finishing like machining or plating. Let's zoom in on step 3 for a second. Compaction. Honestly, it's a lot like packing wet sand into a highly advanced, ultra-high-pressure mold. We're looking at the compression ratio here. That's the volume of the loose powder compared to the volume of the compacted part. Believe it or not, a low compression ratio is actually highly desirable in this step. Why? Well, it means we can use smaller die cavities, there's significantly less breakage and wear on the expensive tooling, and we get much faster die fill rates, which just dramatically speeds up production. Next up, let's look at the precise definition of step 4, sintering. The key phrase here, heated without melting. Remember our sandcastle analogy? We packed the sand tightly, sure, but it's still just fragile, packed powder. Sintering is essentially like baking our packed sandcastle in a highly controlled oven until the individual metal grains physically fuse and weld together. By keeping the temperature just below the melting point, we completely skip the liquid phase. The part solidifies and strengthens without losing its complex engineered shape. Section 4, Safety Risks and Science. So we've got this incredibly efficient green manufacturing process, right? But it hides a pretty volatile twist. Because we're dealing with microscopic metal dust that has a massive overall surface area, the raw material is actually highly explosive if it's mishandled. The safety protocols required here are extreme. Facilities have to ensure all equipment is heavily grounded, they use specialized, non-sparking tools to prevent friction heat, and they strictly avoid kicking up dust clouds or creating open flames. And that leaves us with a truly fascinating paradox to ponder as we wrap up this explainer. We use this exact method to create some of the most heat-resistant, ultra-durable, high-tech jet engine turbine blades capable of withstanding the absolute most punishing forces on the planet. Yet during the manufacturing process, who knew the biggest threat to creating those invincible parts was just a single, tiny stray spark in a cloud of dust? It just goes to show how incredible and incredibly delicate the science of manufacturing truly is.